Hi everybody, welcome to the first of the Strand 7 tutorials for ENGG1500. These are tutorials designed to help people who are currently doing the structures project, that is building the water tower. You've been given the task of designing and constructing a tower to hold a set amount of weight. One of the issues you have when trying to do these types of designs is it's very hard to test experimentally whether one design is better than the other without building both and physically testing them to failure, which is generally not particularly efficient. So one of the things that we use as engineers to help us with our design process is software. The software I'm going to show you is the Strand 7 package. It's what's called a finite element analysis package. What it allows us to do is make a model of our structure. I've modeled a very simple bridge here. So here's my bridge. I've got my model of my bridge, and then I've gone and made it in Strand 7. I've put my loads on it, put my forces on it, and I can watch the way that it deforms under these loads and the way that the stress gets applied in the structure. Now, before I talk about this anymore, I am assuming you have read through the Introduction to Structures notes that should be available on Blackboard for your project, alright? So I'm going to be relying on the fact that you've read through them, and I'm going to throw around my terms like stress and beam and joint, assuming you know what I'm talking about. So if we do look at our structure that we have here, one of the things that we can do is just get rid of the animation, look at it statically. One of the things that we can do is color code our beams based on how much stress is in them. So if I come and I look over here, I can see I've got negative and positive stress, implying tension or compressive stress. But I have a lot of compressive stress in the purple members, that one and that one, and a lot of tensile stress in those members, and a lot of compressive stress in the blue members, the ones around the outside. In the middle here, I've got relatively low stress, and that's these two members in the center. So if this was my initial bridge design, and I wanted to improve upon it, I could know that I could come and probably take material away from these two beams, and I could add it to, say, these three beams here, which are under a lot of stress, and I would end up with a stronger overall structure. Alright, so the use of a software package like this allows us to improve on our designs. It would also allow me to make a completely different design, test the two, and see which one was better. Now, proper use of an FEA package, actually understanding what is happening behind the scenes and knowing all of the functionality that this thing has access to, is certainly not a first year course. You will learn it in third year in civil, third and fourth year in the mechanical engineers. You'll learn to look at this type of stuff in depth. All we're doing here is allowing you to do design modifications, okay? So don't quote these numbers and assume they are perfectly accurate to 8 decimal places. They are not. We've made some big assumptions here. But we can do comparative studies, okay? So what I'm going to do today is take you through the way in which I built this beam, this structure, blow by blow, so that you can build it along with the video. In some of the subsequent tutorials, I'm going to show you a few of the cool tools and things that Strand 7 has available to you, so that you can design your water tower, model it in Strand 7, and come up with, hopefully, the best design. So I'm going to start from scratch. I'm going to get rid of everything here. Close, go away. I've got nothing. If you open up a university computer, hopefully you should be able to come down here and type in Strand 7, and it will come up. Now, because I'm not on the same network as the uni computers, I don't get that option. If you want to be on a personal laptop, you won't get it either, but there is a way to connect anyway. So if you go to File Explorer and you go to this PC over here, you can map the Strand 7 drive provided you're on the Uni network. Okay, so you come and connect to the Uni Wi-Fi or whatever, you'll be able to map the Strand 7 drive. Probably 1 in 10 of the computers, the Uni computers on campus, won't have this Strand 7 working. I don't know why it never seems to work, but we always seem to have problems. So I'm going to show you how to map the drive. All you have to do is come up here to Computer, go to Map Network Drive, type in //Strand/Strand7. Make sure you get the slashes the right way, the same way they are in the example. Hit Finish. And you will get a new network drive. In my case, it was this X drive, which has got Strand 7 in it. Now, you might get asked for a few credentials and asked to log in and things, but that's all you have to do. Come down to your bin folder, go right down the bottom to Strand 7 executable, and Strand 7 should start. As I said, most of you should hopefully be able to find it in here, but if you have any dramas, you can always just do this. Okay, so Strand 7 has started. It looks like this. It does not look like very much at all. There is nothing in it, but we've got the program running. The first thing I'm going to have a quick chat about is our bridge. So this is the thing that I'm going to make the model of in Strand 7. It's the real bridge. Our first step is to convert this from our real structure into our modeled structure. Alright, now this is using all of those techniques that I talk about in the Introduction to Structures document. I've assumed that these are beams, that they're long, thin, slender members, their cross-section doesn't change. I've assumed that they're actually pinned together at all of these locations. They're pin joints. This is a pin joint connection to the ground, and this is a roller connection to the ground. Okay. We've got two loads on here, a 6 kilonewton load and an 8 kilonewton load. So we're looking 14 kilonewtons, meaning 1.4 tons, meaning roughly the weight of a rugby scrum, I suppose you'd say. Both teams in there would weigh about that much, but we've summed them up and put them down as 2 loads. Just to give you an idea of scale, we're talking 9 meters across. This is an important first step, okay? The location of all of these points, which I'm going to call nodes from now on, is important. That's basically what we're going to do, is build these nodes and then join them up by beams. Alright, so knowing all these points in space is super important, and when you do your models for your own towers, knowing these points in space is going to be important for you. Okay, so that's what we're going to try to do. The first thing we want to do in Strand is go new, and it's going to ask us what units we want to be in. You can work in meters and newtons if you would like. That's perfectly fine. That's what I'm going to work in here, because we're making a very large structure. You might, when you're modeling your smaller structure, want to work in newtons, millimeters. So millimeters, newtons, and it's convenient because stress will end up coming out in megapascals, which is roughly where your stresses will come out. If we work in SI units, meters and newtons, a stress is going to come out in pascals, so we're going to have hundreds of millions of pascals. But that's alright, it's just units. I'm going to stick in SI for now. So, okay, accept that. We have our blank space here. So we've got nothing in the world at the moment. The first thing we're going to do is create this node here. I'm going to make node A. So I do that by going create node, and it asks me for an XYZ location of that node, 0, 0, 0. That's where I'm going to put the first one. And now I have a node. It's a little small. I'm just going to make them a little bit bigger. In general, don't do this. You want your nodes to be small, but this is just for the video to make sure that it comes out clearly. I'll just make my nodes a little bit bigger. Alright, so I've got one node there. I'm going to do this the easy but slow way. I'm just going to go in and tap in the coordinates of all of these nodes. Alright, so I'm going to create another node. I know that the next node is at 3 in the X, 0 in the Y, 0 in the Z, and then the next one will be at 6, and then the next one will be at 9. Gives me these 3 nodes here, G, F, and E. I'm now going to go and make B, C, and D. One of the issues is I know when I try to make this node here that in the X it's going to be 1.5 meters because it's going to be in the middle. In the Y direction I don't exactly know where it is yet, and I'm going to have to work that out. Simple Pythagoras is going to do this for me. You're going to equal, that's 3 meters, that's 1.5, and I want the length of that. So you're going to equal 3 squared minus 1.5 squared to the power of 1.5 squared to the power of a half, 2.598. Cool. 2.598. Apply that. 4.5, 2.598. Apply that. 5, 7.5. Okay, there is a smarter way to make these nodes. You've got a whole bunch of tools up here, which are going to allow you to do fancy things and make geometry in a far more efficient way. That's going to be the point of video 2, okay? So I'm going to show you how to do that. It'll save you a bit of time, but I like doing this at the start because you should always remember, if you ever get confused about how to build anything, just do the geometry, work out your nodes in space, and then you've got them, you can just join them up, alright? So getting your nodes is important. At the moment we're not zoomed very well. The graphical interface in Strand is terrible. Okay, I can't just scroll my mouse wheel to zoom in and out. I can't just click and pan around like you normally would. It relies really heavily on hotkeys. So I'm gonna show you a few things that you can do. You've got a zoom in up here. So you can come and draw a box and zoom in on that. Reasonably useful. Probably the most useful is this one here, redraw. So F3, I just learned to always mash F3. After I make any new geometry, it will zoom your screen to contain everything you have made. So if you've been up here looking at this node and you press F3 or redraw, it'll just zoom you back out to just put everything you've made nicely inside the window, which is great. If you want to rotate, you've got this button here, and now you can click and you can rotate around the point. Alright? It's still not great, but it does work. I'm now unfortunately on a weird angle where I don't really want to be. I want to get back to being square. Hitting F3 doesn't really work anymore. I need to hit F12. I don't actually know where this button even is anymore. But if you press F12, you'll get viewing angles window, and you can view from a particular direction, say an XY plane. Apply that, brings me back to square. You pick whatever you want here, isometric views, different planar views, so looking from the bottom. But I want to be in the XY plane. It is annoying, you will figure it out pretty quickly, how to navigate around in Strand, but at the start you might get a bit lost and a bit confused. Don't worry, everybody does. Alright, so I've got my nodes, I've got my points in space. I now need to make my beams which join them together. So we're going to go create again, but we're going to create an element instead of a beam here. An element instead of a node, because our beam is an element. Now we have a whole bunch of different elements here. We've got beams, we've got plates, which cover a two-dimensional area. That's what, if I had to make a roof or a floor, for example, I'd probably make it out of plates. And then we've got these brick elements down here which occupy volume. Don't even worry about bricks. They're for making really complex geometry where you can't make good assumptions, okay? We want to make as many assumptions as we possibly can, meaning we want to use beams wherever we possibly can. So we're going to use beams. A beam, being a one-dimensional element, basically just joins two nodes together. So I start here, I click on this node, I click on that node, and I now have a beam which joins the two up. And all I have to do is connect the dots. Yes, it is that simple. It is primary school. Done. Dots joined. One thing that, again, I will talk about this in a later video, but I just want to show you something very quickly. If I was to delete these two, okay, if I was to create another beam that went from here all the way to here, not joining to this one first, just going straight through, that beam is not actually connected to these two beams at all, okay? It doesn't work that way. You need, if you want a connection point, you need to split your beam up, all right? So come and select this beam. It goes all the way through. It is not talking to that node. This part of the bridge will simply fall through the floor of it. That's bad. So just make sure you join up all of your nodes. One of the other things that you will find very annoying in Strand at the start is selecting things. So I'm currently got beams that I'm talking about trying to select, so I can select my beams. I can't actually select my nodes anymore. I can only select beams. And that's because up here, I've told it I don't want to select nodes. So I can turn it on, and now I can select the node as well as the beam. See, it's gone purple. I can turn beam select off, and now I can only select nodes, and I can't select those beams anymore. The other thing is this button here is the toggle select button. If I take it off, I can't actually select anything at all. You will find this really, really annoying. You'll forever be trying to click on stuff and realizing you have to come up and hit select because Strand has unselected it for some reason. You'll be trying to select beams and not have beam select on. Happens all the time. There is a reason for it. When you get to really complicated structures, you will often only want to select that node and not select all the beams around it. But for you, at this stage, just make sure you've got the right thing selected and be aware that it is an issue. Really useful tool is this one here. This is clear all selections. No matter what, that will just unselect everything in your model. And this is another one of my favorites, select all. If you want to delete all of your beams or whatever, select all is super useful for that. Okay, sorry, that's a bit of a boring thing, but it's super frustrating when you start out with Strand to try to navigate around. Okay, we have our nodes, we've connected them up with beams. Let's go through and put these loads and these restraints in, because we haven't done that yet. So the loads are point loads, which means they act on a node, which in Strand means they are an attribute of a node is a force. Okay, I will do another video talking about attributes later. All you need to know now, node, attribute, force. We've got this node here has 6 kilonewtons going downwards, so that's going to be minus 6,000 newtons. If you come down here into this corner, you can see your coordinate system, and that's telling us that positive y is pointing up, x is pointing to the right, and z is coming out of the page. So that's how I know this is negative 6,000. Points down. This one over here is going to be 8,000, negative 8,000. If, for example, I didn't have the negative in, it would point up. That's fine. You will get directions wrong all the time. Don't stress. Just put them in. See what happens. You can always change them later. When you apply, this is another trap for young players. If you take a node with a force on it, and say I was to change this to be 20 positive, and I apply this, it will overwrite the 8,000 newtons that was on it. Okay, that overwrites it. It doesn't add it. If you have your minus 8,000, no nodes were selected. I want that node. And then you decided you wanted to put a horizontal force on it as well, of 20. You can add that, okay? And now you get a horizontal force without overriding the vertical force that was on there. But if you don't want to do that, if you've made a mistake with forces and whatnot, just come in, put the right number, hit apply, and it will all work out. That was me pressing F3 again just to redraw, so I just redrew my model, and it will relatively scale the length of our force arrows so that that one is longer than, that one is shorter than that one because that's a smaller force, which is nice. It helps you do logic checks, making sure that you didn't accidentally put an extra 0 in here or something like that. Alright, most of what we have is there. We need to do our restraints. That's what we were going to do next. So that's got to be a restraint, and that's got to be a restraint to stop this thing flying off into space. So again, it's an attribute of a node is a restraint. Okay? This node here, basically what we're doing with a restraint is fixing degrees of freedom. So we're stopping it from moving. So if this is a pinned joint, it means that these beams can't move effectively. Okay, so it locks them in place. So we don't want it to move in the X, so we want to fix its translation to 0. We don't want it to move in the Y, we want to fix its translation to 0. And we don't want it to move in and out of the page, so we're going to fix that translation too. So that node can't move up, down, left, right, in or out, which is great. We didn't want it to. What we do have to be careful of though, this is a pin joint, so it can rotate. Okay, so this whole thing can rotate around this way. So that's that Z-axis there. We do not want to hold that degree of freedom. We want to leave that free. We do want to hold the other two. They're going to stop it rotating in and out of the page. Okay, so we've got all of them. We can apply that. It'll show some lines there. Pink are for translations and white is for rotations. It's put some restraints on. We want to come over to this guy over here, select it, have a look at our pictures again. Oh, I closed them. Not what I meant to do. Give me 1 second, I'll get our pictures back up. 1500 projects, civil, water tower, truss bridge. There. This is our roller joint over here. So it's not restrained from motion in the X direction. This point E can roll side to side quite happily. So we want to enforce that, well, we want to allow that, so we want to get rid of our X restraint. So basically when we apply this, this node should be able to move in the XY direction. Cool, so far so good. We've got pretty much everything on here. We've built all of our geometry, we've put our forces in, we've put our restraints in. What we haven't done yet is actually told it what these beams are made out of, and that's because that's not actually anywhere on this drawing. So I'm going to show you how to do it, but I'm going to just put in some notional numbers. So these are all beams, our blue ones here. What we do is we go property of a beam, and we can come in and we can tell Strand what our beams are made out of and how big they are. So Strand wants to know a whole bunch of things about our structure. It wants to know predominantly what the Young's modulus is and a Poisson's ratio, a few material properties. So Young's modulus, that just the modulus here is stiffness. And if we go and look up the stiffness of the materials that it is that we wish to use, whatever they are, our concretes, our steels, aluminium, whatever, we can put that number in there. Luckily Strand has a library that has a lot of materials in it. So I just come to materials and I get my huge big library here. There's some weird things in there, like bone and wood and stuff. Glass, not really a common structural material. But we do have our aluminium alloys, we've got concretes, and we've got structural steels. Probably the most commonly used building materials. So we can come into steel, pick structural steel here, it's a common one, that's great, and it will auto-fill this type of stuff in for us. Modulus is 200 gigapascals. That's a lot of zeros, that's pretty annoying to work in, and that's why we use this scientific notation. But it's also why, when I said pascals aren't always the best unit to work in, that's why. We also need to give our structure some geometry. So the two tabs that you have to do all the time for every beam property type that you have, and you might have more than one, but we've only got one, but you might have more than one, you need to give it structural information and you need to give it geometry. Okay, all the rest of this heat, non-linear information, not required for what you're going to do, but you have to give it structural, you have to give it geometry. So if we come to geometry and we come to edit, we have a whole bunch of common beam cross sections in here. So if you've got I-beams, if you've got pipe, if you've got RHS, which is what I'm going to build this out of, you can come and you can put your numbers, you can come and select that as geometry. So I'm going to select RHS. It's coming and asking me for my dimensions. I'm going to make it out of 25 mil by 25 mil RHS, 0.025, 0.25. This is important. People get this wrong all the time. I still do it every now and then. Come here and write, oh, it's 25 by 25 RHS. Yeah, that's meters. That's not going to work. This happens a lot with structural stuff. You measure the length of it in meters and the cross sections in millimeters. Can cause a lot of confusion. If you've ever got a really weird looking model, come and check that you didn't get these wrong. So 25 mil by 25 mil with a 3 mil wall thickness. I'm just kind of making these numbers up. This will be something that we might want to refine later. So we're going to assign that. I'm going to solve this as it is, and then I'm going to come back and talk about what this is on the side. I'll talk about it now actually. If you leave this selected as beam, it's assuming that all of these are welded connections or rigid connections, okay? If you change that to truss, it now assumes that all of these are pin joints, okay? These are pin joints. The way that they're represented on the diagram would definitely imply pin joints to me. If you've done all of this, you can solve either way, okay? Beam or truss, but it will change your results, so be careful about what you're doing. In actual fact, when you're looking at your models of your own water towers, it won't be clear to you whether you have beams or whether you have trusses. It might cause a bit of confusion. You should probably solve for both and try to find a worst case scenario and design around that. Okay, so I'm going to leave them as beams for now. I'm going to hit F3 to redraw. I'm going to redraw. And it's come and drawn in our geometry for us. Now I'm going to just show you something else. I'm going to zoom in on one of our joints. So I'm going to zoom in up here. Okay. So the model is pretty terrible around the joints. This is not how you would build this structure. But we've told Strand that that's a welded connection, and it doesn't need any more information than that. It's going to just assume that that's a welded connection there, okay? So you don't have to worry about the fact that it doesn't look right. It will solve correctly based on the assumptions that we've made. Okay, so we've got our structure. The only thing we've got left to do is solve. So we can come up to solver, go linear static, save it somewhere logical, Strand 7 tutorials. Let's go shoot one, save and solve, and it's solved. All right, so it does not take very long. Solution time was 1 second. It's very, very powerful tool. It can solve things far, far more complicated than this very, very quickly. We've got a solution, so we can close that, and we can come and open our results file. Okay, so that's over here, open results file. It will ask me which results file I want to open, the only one that I have in this case, open. Now it looks exactly the same, but I've got some different icons up here that I didn't have before. What I can now do is come in and, for example, go to my result settings, say I want to use contour of stress, and now it's going to ask whether I want to look at the axial stress or a bending stress. Total fiber is a summed stress, okay? So that's going to do a summation of compressors and tensiles and bendings and this, that, and everything else you can think of. All of that gets summed together in a total fiber stress. Use that one, is basically what I'm saying. So contours of stress, total fiber, apply, okay, and we can look at the stress in our structure. So again, we can come in and go, we've got a minimum down here of 33 megapascals, maximum of 32 megapascals. This is always going to represent itself in scientific notation, so make sure you're coming in checking the exponent here. Yes, that is 8, but it's 8 by 10 to the 6. This is 3 by 10 to the 7. So get used to coming in checking this. Again, pascals, not great units. Megapascals, much more useful. But 32 megapascals, 33 megapascals, most of the stress is being held in that and that member. So these ones are on the outside, and then these three through the middle. These guys are doing basically nothing, and these two are holding a little bit of load, but not heaps. So that's cool. We've got to solve. Basically, this is excellent. We've solved the structure, and we can now analyze it and figure things out. Go and redesign, go and compare this design to another design and look for the maximum stress that we've made. Try to work out how much load we think this thing could take before something would break in our structure. Another thing that we can do here is use this displacement scale. So what this will do is artificially move. So what I might do first, I'll go the other way around. I'll go contours of displacement, d, x, y, z. So this is going to give me how far everything has moved. Actually, I'll just go dy, like that. Okay, this is how far things have moved down. So how far in the y direction everything has moved. Because if we load this bridge up, obviously it's going to predominantly just sag in the middle, right? It moved at most 2 millimeters. That was our deflection. 2 by 10 to the minus 3, we're in meters, so it moved 2 mil, and this thing is 12 mil long. There's no way that you could even see that, like not at all. So what we tend to do instead is, if we want to have a look at what is bending in our structure, we amplify all of these displacements to something more reasonable. So come and put a displacement scale in of say 5 or 10% is generally good. Hit OK, and it will just artificially bend everything for us. So that is not what our bridge would actually look like, but it does allow me to see that yes, it is sagging in the middle the way that it's supposed to. You might want to do this to see how much, say, your water tower is going to deflect, see if you can figure out which beams might be moving, whether you wanted them to or not. But predominantly it's useful to make sure that your whole model was joined together the way that you thought it was, and that it bent the way that you thought it did. You can animate this, so if you go right click, animation, 8 frames is normally enough. You can turn it up if you want, it doesn't really matter. It will show you how your structure deforms under load. Probably the most useful thing to check here is your restraints. That is supposed to be a pin joint, so it's not meant to move in the XY, but it is meant to allow rotation, which is exactly what it's doing. This is a roller joint, it is meant to be allowed to move in the XY, which is exactly what it's doing. Is allowed to move in the X, not allowed to move in the Y, sorry, which is exactly what it is doing. So that's good. You should always spend a fair bit of time looking at this type of stuff with your models, because it will prevent you from making mistakes, okay? But overall, we have a structure now. What I would advise you to do at this stage is go through and build it, get to here, get to where I am. You may have a bit of trouble with it. It may take you quite a long time. This is normally something that I expect to take you a good solid 2 hours to do properly. So if it is taking you a while, don't worry. But once you've built your structure and you've got to here, the next thing that you should do is close your results file and go back to this window, which is your build window. This is where you were before. This will allow you to change geometry and start changing things. You can't hurt it, it's a simulation. So have a go at things. Come into property, change it to a truss, see what changes. Do another solve. You got to do another solve every time, okay? Yes, I'll overwrite my old file. Great. Warnings you will get, that's okay. Errors are not okay. If you get errors, that's very bad. It means generally that you've missed a property somewhere. You haven't filled in a geometry or a modulus or something like that. Or you had, say, beam property type 2 in here. Or you haven't restrained your model properly. Alright, so if you ever get warnings, don't be super worried. If you get errors, be very, very worried. Go back, fix your model. Open your results file. Have a look at how things have changed now that I've made this a pin jointed structure. The super obvious one that I'm hoping you're noticing is these things aren't bending anymore. They're all straight because they're pin joints, so they can't hold an axial load. So they can they can't hold a bending moment, so they only have axial loads. So they have to be straight. There's no bending anymore. Deformation of the structures. Has it changed? Is it the same? Come and have a look at your stresses. Is it more? Is it less than it was before? Did it make a difference? They're really similar, it turns out, in both stresses and deflections by the look of this. But these are things that you can come and investigate. Change that from a roller to a pin joint. Change it to a rigid joint. Change, play, do whatever you want. Get familiar with the software. The only other thing that I will show you how to do, we've discovered that these two members aren't doing a lot for us, and these ones around the outside are doing a lot. We can come back and select that one and delete them, and we can create an element of property type 2, so a different beam property type. That will be red. Beam property type 2. We can change them, say, to be an aluminium alloy. We can change them from being RHS to being flat bar. 25 by 5 flat bar, for example. now we've got some pieces of flat bar in there. There you go, bit of flat bar instead of a bit of RHS. And overall this will have, say, made my structure lighter. And you can now go and resolve and we can look at stress, and we can see that they're still not even maximum stressed elements. So we just cut a whole heap of weight out of our structure and it's still nice and strong. You can then go through, maybe thicken up these other elements, do whatever it is that you want. Alright, so have a bit of a play, get familiar with the software. The following tutorials will help you to understand some of the tools that you're going to be using and a bit more about navigating around in Strand. Alright, good luck.